Yes, welcome all. Combinatorics of posets, lecture number 3. We start first with the proof of the theorem that we stated and discussed at the end of the last lecture. So the statement is here above. The theorem is that we're given a poset P of height close h, and all we know about this poset besides that is that the weak coloring number of its cover graph is small, which weak coloring number 3h minus 3 actually, is bounded by something that we know, c. Then the dimension is bounded in terms of c, and the bound is 4 to the c. Yes, this is interesting for the reasons I already told you, and for some reasons that I will tell you today. So we do the proof of it. For the proof, let's see be this weak coloring number, and then fix a linear order on the vertices of G that witnesses the value of this weak coloring number. We call this order pi. So the thing is that whenever you look at the vertex V and you look at its weakly reachable set with 3h minus 3 steps at most, then the number of vertices you can reach this way is at most c. And then, given the pi, we do the greedy coloring along pi. So we go one by one, we look at the vertices and we apply the smallest possible color such that you avoid coloring the vertex, you avoid colors of all the colors that appear on its weakly reachable set 3h minus 3. Yes, this way you use at most c colors. It's a C coloring. And then there is this easy observation combining two witnessing paths. So whenever you have vertex x in the poset and you have two vertices yz such that they can be reached from x with a small number of steps, h minus 1 at most, then and given that these two vertices are distinct, then one of them can be reached from the other in a number of steps which is twice the number of the initial number of steps. Yes, so either y can be reached from z or z can be reached from y, and therefore since our coloring was going along was looking at these sets 3h minus 3, at the moment that you were coloring the second, you were avoiding the color of the first, so the colors are distinct. And then we try to relate all this to the poset, because so far we were just talking about a cover graph. So looking at the poset relation, we can define something like a weak upset of an element and weak downset, respectively. So for the weak upset, you take elements y that are in the poset and that are actually above x. So this is really some part of the upset, yes? So given x, you look at the upset of x, but you don't take everything. What you take are those elements that you have a covering chain from x up to y, such that when you look at this covering chain, how does it look like on pi? The final vertex is the leftmost one. So this means that perhaps you take element y here, because of this chain here, and then when say this is pi, so this would have to be x, and then you look at this chain and maybe it looks like this, and you see y, So if this is how this chain projects, it's important that we take covering chains, which means that the steps we take are cover relations, so we can see this chain projecting to the path on the cover graph. Yes. So as you see, not necessarily all the vertices on this path on this chain on the upset would belong to the weak upset, because some of them, for example, are just right of x. Also, this element here is not necessarily in the weak upset. At least this chain wouldn't be a witness for that. Yes, so that's a weak upset, and you also have weak downset, which is a pretty much symmetric definition here.
Excuse So that chain has to be in the cover graph, not in the comparability graph.
Yes, in the cover graph, definitely, definitely. Yes, yes. So yes, but whenever two elements are comparable, you can walk in a cover graph, respecting relation from one to the other. Yes.
Yeah, but that path.
Yes, yes. So
Yeah.
that's what I mean by covering chain. Yeah, which is kind of maximal between the two. Yes. Okay, okay, okay. So that's the thing, and then easy thing to observe is that both weak upset and weak downset of an element is a subset of the things you can reach from this element in 8-1 steps. That's pretty clear. Yes, and then one more thing we need before we state the critical, before we start to partition incomparable pairs of the poset, is that when you look at a single element X, you take your favorite color, which appears on the weak upset of X, color of an element. Then by observation stated before, this color appears exactly once. Yes, and this is indeed true, because if I have an orange element and I would have another orange element and both of them are in the weak upset, then these two witnessing paths witnessing that they are in the weak upset combined would give us that one is reachable from the other, and so they cannot have the same color under our coloring. So as such, whenever we have this element and whenever we know that the color appears, we can point to an element, and this is the element of color I in the weak upset of X, and this is the element, if I is there, in the weak downset, yeah, of color I. Okay, so that's almost everything we did at the end of the last lecture. What we should proceed with is it's already a partitioning of a set of incomparable pairs. Yes. So given an element xy, an incomparable pair in P, we define a signature of xi to be a triple ABC, such that A is just the set of all colors that you see in the weak offset of X. B is the set of colors that you see in the weak offset of X intersected with the set of colors that you see in the weak downset of Y. And C is yet the subset of B. Among those colors that are in B, you take those that the two witnessing elements are in some fixed ordering in pi, so this element carrying color I in the weak upset and this element coloring color I in the weak downset of X and Y respectively are in this relation in pi. So that's a signature of an incomparable pair, and the claim is that for every ABC possible evaluation of a signature, all pairs, set of all pairs with signature ABC is reversible. And since the number of possible signatures is exactly 4 to the C, this will close the proof. That's easy. I think I mentioned that yesterday, right? So the number of triples that satisfy this is exactly 4 to the C, because we do nothing else but for color the base set, which is this, yeah? So indeed, this claim gives us the theorem. Okay, so we enter the proof of the claim. So the claim says that the set is reversible. Suppose the opposite. So the set contains an alternating cycle. Maybe we don't need it to be strict, we'll see. Consider x1, y1, xk, yk, an alternating cycle. Yeah, so fix, of course, ABC, right? An alternating cycle with all pairs of signature ABC. And we have to come to the conclusion that this is not going to work well, right? What do we do? So a quick reminder, an alternating cycle is this animal that sends these incomparable these comparabilities, and then at the very end you send this one, yes? So this is x2, y2. Now, so what do I want to say? So for each j in k is the length of my alternating cycle. I have xj less or equal than yj plus 1 cyclically, yes? In B. So what do I do? So this is say xj, and this is yj plus 1. So I have some covering chains, yeah, at least one, starting from xj and going to yj plus 1. Among all such covering chains, I pick one such that it reaches leftmost in pi. So we should have a look at pi now. And I don't know where is xj and yj plus 1 with respect to each other. I'll make some assumptions just to make this meaningful. So maybe this looks like this. But then there are some ways to get from xj to yj plus 1. Yeah, so maybe there is a path that looks like this, yes? And I would like this path if this element here is leftmost possible. And then this path from xj to yj plus 1 will be called qj. And this element that is leftmost will be also qj. Okay? So qj is the minimum on pi of qj. Now you know we have k such paths, and we have an alternating cycle that is cyclic. So we can assume that q1 is leftmost among all q's. Because so say q1 is less or equal in pi than all the q1 as well up to qk. Yeah. Okay. Q1. So let's fix the color of Q1. T is the color of Q1, and then to have some narrative let's say it's orange. T is orange, okay? What do we know? Well, what was Q1? Remember, you should, it was 1 minute ago, that Q1 was a path from x1 to y2, yes? Some special path. Q1 lies somewhere on the way. x1 less or equal Q1 less or equal y2 in P. Yeah? So, what else do we know? I want to say that we know that Q1 is in the colors of the weak upset of x1. Yeah, because it's in the upset and it's leftmost on some path starting from x1. So it's in the in the colors of the weak upset, yes. I also want to say that Q1 is in the colors of the weak downset of y2. The same story. It is on a chain starting from y2 and going down in the poset, and it's leftmost on pi on this chain. Yeah. Okay. So now, you know, our pairs x1, y1, x1, xk, yk have the same signature, ABC. What A stands for in the signature? It's this set here. This set is the same for all x's. Yeah? So this set here is A. So in particular, yeah, I know that Q1 is in the weak upset among the colors of in the weak upset of the x2, not x1 but x2, because it's the same set. Yes. Why do I say Q1? By the way, if I talk about colors, I should. Yeah, if it's Q1, then it's just this. Yes. It's an element, right? Okay. But maybe, we'll see what I need. But maybe this whole discussion was about T, and then I have colors, right? And this is A. But now, what I want to say is that since T is in A, and A is the same as the weak upset of x2, yeah, I do know that T is here, because they have the same signature. And it's also here, nothing changed, y2. Yeah? But this set, the intersection of these colors and these colors, is the second set in the signature of x2, y2. So, and all of them are the same. This is B. Yeah? Okay, so we know that T is in B. So in particular, these elements W, UT, or any xi exists, and W, dt, for any yi exists. So now the proof splits into two symmetric cases, and basically it is about if T is in C or not. But more like descriptive, it's about the relation of WUT U, so of x2, and WDT of y2. Yeah, both of them exist. Yeah, and I don't know how do they relate in pi. If they relate this way, then this is equivalent to say that T is in C. And in the other ways, then T is not in C. So let's assume that this is this way. So I could also say that T is in C, yes? How do we proceed? W U T x2 is less than W D T y2 in pi. W D T y2 is exactly Q1 by definition, because that's the guy on the path, and it was leftmost possible, yeah, among elements that could appear on such paths. So this is by definition Q1.
Can you just say it's because the color's unique?
Yes, true. This also should work here. And by the choice of Q1, this is less or equal than Q2, which is by definition the minimum pi on pi on the path Q2. Everything is in pi here, right? Okay, so now we are getting there. So what do I want to have? 3 items and 3 paths to consider on the final drawing. So one is between WU2 x2 and x2. So this guy is h-1 weakly reachable from x2. Yeah. So how do I draw it? Well, I have x2 and I have WU2 UT. Sorry, x2. And by the definition of this element, there is a path, yes? Let's not make it too messy. Maybe like this, okay? So this path has at most h-1 edges because we are walking in the upset of x2. Another path that I want to take, also this style, connects WDT y3 and y3, right? Right. So I don't really know where is x2 and y3 with respect to each other. This is not important for the argument, but since I want to visualize something, I will draw it, and let's just say it's here, right? And then the WDTY3, the same story, so perhaps it's here. And now I take another path. So yeah. The last path is Q2. It connects x2 with y3. This is this relation in the alternating cycle. I don't know much about this path, yeah? I know that its minimal element is Q2, and we should relate to it in a moment. And Q will look, I don't know, something like this. Yeah. This is Q2. Which guy is oh my god. There is a pi here, right? I assume that WUT is left of WDT, yet here I draw the different way. Correct?
But here it's written y3.
Ah, it's y3. Okay, so it's okay. So it's okay. Sorry? So I know that WUT x2 is less than WDT y2 which is exactly Q1, which is less or equal than Q2. Yeah? So what do we know? This guy is orange. Where's my orange? Yeah, it's the T. This guy is orange. The yellow is the kind of reachable path from some vertex here. Blue the same from some vertex here. White I have not so much control, but I know that the highest, the leftmost element of white is right of this guy. Therefore I know that among all the union of the three paths, one of these two is the leftmost. And this means that from the one that is right, if I start walking, I'll get to the one which is left in a number of steps which is at most 3h minus 3. And I reach it. Is it game over? Given that these two elements are different, it's game over, because then I cannot reach one from the other, and they are still of the same color. So maybe they are the same. But what goes wrong then? If they are the same, I can walk from x2, enter this, there is a teleport now, and get to y3. So I'm on the path from x2 to y3. But Q2 is right of me, and Q2 by definition should be the thing which is the leftmost among everything that I can do walking from x2 to y3, and that's the final contradiction. Okay, are there some questions related to the proof or to life in general? Yes?
If you combine those two paths, are they still short enough?
If I combine which two?
The blue one and the yellow one.
Are they what?
Short enough.
Well, all three paths are of size at most h minus 1. I think you relate to the last argument,
Yes.
where I walk from x2 to y3. But there I just say that I'm on the chain up. I don't care what is the length. And someone told me at the beginning that the height is h, so it's no problem. But
Okay, actually.
but it's,
But why is the white path at most h minus 1? The length of it.
so what was white? Well, white was the chain from x2 to y3,
Yes.
specifically chosen. So it's a chain. It's at most h minus 1 edges. All three are chains, and as such, the number of edges is at most h minus 1 each, because the height of the poset is h.
Yeah.
Did it help? I'll let you time
I'm just
to
wondering whether if I take the blue one and the yellow one together, that is also a valid chain for choosing Q2.
well, when you were considering Q2, or in general any Qi, you were looking at all the chains from xi to yi plus 1, absolutely everything. Each such, absolutely everything, yes?
But then I don't know whether the white one, which hits Q2, is
The white one, well, the white one is Q. The white one,
doesn't matter.
It-
Okay, I see.
It's okay, it's okay. Hong?
Can you just repeat the part where if they're the same, then what's the problem?
Yes, so if these two elements are the same, we should recognize that on the picture we have a chain from x2 to y3 that is different than what we expect. So one chain is in the picture is the white one, but this is not the one. The other is blue connected with yellow, given that this coincides. Yeah, blue walks up in the poset from x2 and hits this element. And it happens is this element you can still continue to walk up towards y3. And the problem is that this chain reaches more to the left than Q2, which supposedly was the leftmost ever in this setup.
So is there one more case remaining to the proof, or?
Yes. So that was assuming this, that the ordering of these elements is this in pi. Obviously, it could go the other way around, and then the proof is symmetric, and the key idea is that in the alternating cycle, look what I did here. I walked towards y3, I should go the other direction in the alternating cycle. It's symmetric using the fact that I can consider the other direction in the alternating cycle and get the same contradiction. I know this is kind of a bit confusing, but it's really the same argument. Yeah, and so this should be fine as soon as we digest this well, yes?
Don't you miss the case where actually you have equality there? Because you said one case is when they are smaller in pi, second case if they are larger in pi. And if they are equal, you need to say that they are actually the same guy because both of them have color T. And then you have x2 and y2 being comparable.
Now the proof is complete. I missed it. Rose?
So presumably you know that the dimension is not bounded if you look at the weak coloring numbers of just height h minus 1. Like I think it's natural to ask if you look at directed paths and only count those vertices in the for the weak coloring number, as in count the weak upset plus the size of the weak downset as the size of the weak coloring number, if this works. And the proof is somehow close because you have just 3 paths that are directed.
Well, I didn't get the question.
Yeah, so I guess 2 questions. If you, instead of looking at the weak coloring number of height of radius 3h minus 3,
yes,
if you look at it of just h minus 1, presumably this isn't enough?
Yes, I remember I was trying to understand how large, which weak coloring number I need to take. I really don't remember the conclusions. I had some understanding that I need to reach something. I don't remember the examples now. Maybe I'm not sure if 3h minus 3 is the. Yeah, that's a valid question. Maybe 2h is enough, for example, or something like that.
And then
even
the
h.
other related question was if you only count vertices that are weakly reachable via a directed path in some direction. That's presumably also not enough.
If I only count the vertices that are,
But you're composing the 2 paths in the observation argument. They're going one path backwards than the other. So
Yeah. So I wouldn't expect it to work for this sort of
at least
reason.
this
So I was
argument
wondering
relies on
if
the,
that example-
to have this more general setup. Now, thanks, now I understand the question, sorry. I'm slow. Yeah, I would say that it's very unlikely that you would get a positive conclusion here. My intuition. Still, we would need to discuss the example, but this is very unlikely to be true. Yeah. The right parameter. Yes, this could be actually interesting to see if you really need this one. It's a very technical, specific question, of course, but it's valid, and I did some effort some time ago, and yeah.
I think that answers the question.
Somehow, you know, this all. So as most of you know, weak coloring numbers capture some notion of sparsity, and we are proving here actually that when you have a fixed class of graphs of bounded expansion, then posets with cover graphs in that class have a dimension bounded in their height. This is not the first proof of this statement that we had, and by far it's the simplest. Really, weak coloring numbers did the job, and yeah. So that was my context. I was so happy that this is so simple that I didn't ask if I really need all the pieces properly. Yeah. Okay. So the theme of today's lecture, or at least a substantial part of it, is dimensional sparsity. And the main leverage is the theorem that we just proved. So here's a question. There are 2 free natural lines of research, and we have some results already proven here that will fit the picture here and there. So the first natural question is, given these examples that we've seen, is when the dimension actually is absolutely bounded, what do we need to forbid? Yes, and since we've seen like planar cover graphs, outer planar cover graphs, yeah. Let's talk about forbidding things in terms of the minor in a cover graph. And so rephrasing, if I tell you that I have a family of posets with large unbounded dimension, which minors are unavoidable? What is forced? So we know something, right? We know that when a cover graph is a forest, dimension is at most 3. When it's outer planar, dimension is at most 4. When it's planar, yeah, it could be unbounded, even when you tell me that the trio is 3, because that's Kelly example. Yes. So yes, K3 is forced. If we have large dimension, K3 as a minor is forced. Yeah, you need to have a cycle in a cover graph. K4 is actually also forced. Yes, K4 minor 3 graphs coincide with 3 with 2. 3 with at most 2, and Michał gave a really nice slick proof that the dimension there is bounded by 12. We knew that it's bounded before, but it wasn't slick, and the constant was way above the limit. So K4 is also forced. K5 is not forced. So, as you see, our reference point is a Kelly example here. If we want to see something forced, it has to appear here. Yeah? If K5 is not here, so it's not forced. Yes. So it's very natural to look at some objects here and think if they are forced or not. Yeah, like a ladder. In the Kelly family, we can have arbitrary long ladders. They are forced. If you consider a poset with cover graphs that have no LK minor, where LK is a ladder of length k, then dimension is bounded by a function of k. This is actually this result came with a project that I really like, for a reason that like 80% of the paper is graph theory. The statements, arguments, it's graph theory. The techniques are coming from the structural graph theory. And this part about posets is this long, because when you get the result, what do we kind of develop there? That there is a notion of centered colorings, yeah, of graphs. This coincides with 3-dep actually, yeah. But this 3-dep, yeah, or centered coloring number is tied together with the size of the longest path that you see in the graph. And we kind of understood what is tied together with the size of the longest ladder that you find in the graph as a minor. And this is what we call a two-connected centered coloring number. And
Is this ladder somehow dual of standard example in terms of?
it's not dual. You would need to have a click
Not
here.
like complement.
You would need to have a click here.
Oh, of course.
Okay. Here is a really wild conjecture. So something is unavoidable if it's in Kelly. And ladder was a step towards it. And it's kind of tough to make a next step. One thing that we have in mind is a ladder of K4s. So a graph that looks like this. We would like to see this forced. This appears as a minor in Kelly. You've seen the ladder I did on the first half. On the second half I can do the diagonals.
Is the backwards implication true, or neither of them is known to hold?
Well, the backwards is the thing I had in mind now, discussing it with you. So the one from the bottom to up, yeah? If something, you see something in Kelly, if it's really unavoidable. Well, it appears in Kelly, but maybe there is some other construction that avoids it, yeah? So this is the thing I don't know what is the status of this with respect to this in this direction. The other direction,
Well, if something is unavoidable, then it must appear in Kelly, because Kelly
Yes.
has arbitrary dimension.
Yes,
Okay,
yes,
this is
yes.
okay.
There are
This
two
one is-
negations
this
here in
one
the
is-
statement, so I also had to
Yeah, okay.
take a breath, but
The one is easy. Okay.
one is trivial, yes, one is trivial. Yeah, it would be beautiful if it's true. So a little bit of sideline here. So we have some bounds, yes. I presented you like maybe the project itself, but there are specific bounds, and of course you can ask if they are tight. Lots of them are tight, yeah. So for the forest dimension, that spider has dimension 3, so 3 is tight. For outer planar graphs, we did an exercise yesterday. Dimension 4 is tight. 3 with 2, well, 12 is a double-digit number. It cannot be tight, but we don't know anything besides 4, besides the outer planar example. Yeah. When a cover graph is path width at most 2, note that if path width is at least 3, again Kelly kills it. When path width is at most 2, it's bounded, and the bound is slightly better than in the 3 with 2 case. It's 6. It's in Veit's dissertation. Again, the lower bound is 4. Yes, so I close this line of discussion of this line of research here. But by far it's not closed, yes? Another one, Hong?
Just one last question.
Yes.
The main thing that makes Kelly have a high dimension is the standard example, right?
Right.
And is there really no other constructions?
Oh, that's an excellent question. I will come to that. Yeah, it's. I wish to know this. I will come to that. So another line of research here is investigating dimension when height is given. Yes, and this obviously is inspired by the striped rotor result. Yeah, so large dimensional planar posets must be tall, and the bound. The original bound was something scary, and but the proof of weak coloring numbers give you a single exponential upper bound, and we can do better. You can get a polynomial, which at the moment is cubic. We even maybe have some ideas to get quadratic. It would be really interesting to see it linear. We are even not sure if it's true. I'll discuss examples in a moment. But first thing I want to tell you, I don't want to skip the fact that it's polynomial. Look at this easy construction. Yeah, I have a family of posets indexed by even natural numbers. Yeah, P2, what it is everyone sees. And then when you make a step, yeah, you take, you have some incomparable pairs highlighted, yeah, in P2, these are the two. In PH minus 2, you have H, you have lots of them actually. And then for each pair like this, you attach this gadget. Okay? What do you get? The height is H. Yes, and each step the height grows by 2. Exactly. Yeah, you start with P2, which has height 2, and in each step the height grows it additively by 2. The size of a standard example that you see doubles. Yes, because instead of these elements that induce a standard example by induction, you can take the new elements. It's twice more. Yeah, they are incomparable, and yet you have all possible other comparabilities by transitivity.
Excuse me, so you are replacing that incomparable pair that is connected with red dash line with these two?
Not replacing, I attach to it a gadget. This still stays. Yeah, so maybe I draw you P4.
Okay.
So this is P2, it's just S2, yeah. And now I attach this guy here, this guy here, this guy here, this guy here, yeah. And what are the extra? So this guy here is below both of these, yes. At the moment it is incomparable with both of these, but I want to send the comparability here. Yeah, and this I want to send here. This here, this here. I complete S4 this way. And then the next step is that for each here, yeah, I extend it. Okay? And that will be P8.
There's more, right? You also have those diagonal pairs which are incomparable, or
No. Just for these, just for the vertical pairs I do. I keep in my understanding what are the vertical pairs. In P2 I highlighted them, okay. And then in the new structure this is vertical, yeah. So the number of vertical pairs doubles, and they form a standard example. So the standard example number doubles. So we have a height H poset that has dimension at least 2 to the H over 2. Exponential dimension and height. Why is it relevant? Well, it's pretty close to be planar. We don't have K5 here as a minor in the Koppe graph. We even the tree width is 3. Yeah. Maybe I can even argue that on a good day. So how would you? For the P2, yeah, I have A1, B1, A2, B2. I need to have a tree decomposition. Well, let's take A1, B2. This does this edge. I also want to put B1 here for a reason I will tell you in a moment. That's one bag. And then the other bag I will do A2. I need to do B1 and I also put B2. So this is a legal tree decomposition of this graph that both edges are done. It has width 3. And I have an extra condition that I want to keep on the way, that for every vertical pair there is a bag that both elements appear there. Note that they don't, it wouldn't have, it's not necessary because there is no edge there, so it's not forced by the tree decomposition, but I want to keep it. Yeah, so for A1, B1, A1, B1 is here and A2, B2 is in this bag. Yeah, and then when we proceed, yeah, so what is happening? There is a vertical pair. Yeah. AI, BI, yeah, and we attach 4 elements related to that. The new edges, what are the new edges with the old of the new elements? Yeah, well, there are edges attached to the old elements, and there are 2 extra edges, these kind of edges, right? So how do we have a tree decomposition from behind? There is a bag AI where AI and BI is sitting in. Yeah, so I want to create, I think, 3 more bags that I will attach this way to the tree decomposition itself, which is here, right? How do we do it? We need some names. So C1, C2, D1, D2. How do we do it? So I guess one of those has to be everywhere. AI, AI, AI. Now, let's put C1 here and here. How do we proceed? Let's put, say we put D1 here. So this would be the bag C1, D1, by the way. If I put D1, I need an edge to C2. So let's have C2 here. Yes, so I need C2 here. So this should be, here I should have D2. Did I already fail? No, A to C1, A to C2 is done. B, where does B go? I guess BI, I need BI here. Can we complete it? I was sure that I can complete it on the fly. D2, so C2 should be here. So this will be the bag for C2, D2. Now I just need to look at the edges. So C2 goes to D1. I missed D1. C2, D1 is here. C1, D2. That's what I missed. So I put C1 here and I hope that it works. But it doesn't, right? Because DI, D1, D2. Ah! Come on. This should be so easy.
Because C1 and C2, then you can connect AI from lower bags.
So you would do this. Okay, good idea. And I have space. So I use this space to produce B. So should I put B1 here and here? And now it works? Yes. Whew, thank you. Thank you. Okay, apologies for this being a little bit slow here. But where's the message? It doesn't have K5 minor, and dimension explodes. It's exponential in height. So the fact that that it's polynomial really works with the planarity. And that's how these arguments look like. Okay.
May I have a question?
Yes, sure.
So this example that you just showed, it has bounded tree depth, right? Tree depth like for h, I think, right? Because you can iteratively eliminate those guys down the tree. Yeah.
Yes.
So it is true that the dimension is bounded by a function of tree depth.
No.
Because it follows, I think, from your result.
Yes, it is.
Because you don't have a long path, so you have
Independent of height, right?
Yeah,
Just
independent of height.
Yes,
because
yes.
height is bounded by the function
Of course.
of tree depth because you don't have long paths.
Of course, of course.
So this shows that this needs to be a piece exponential, but are there known tighter bounds?
Yes, yes, there is exponential upper bound here.
Okay.
And it is the first thing that would come to your mind. Okay, here is another line of the story. There is a linear upper bound. Dimension is at most 192 times the height, plus something innocent. What's the tweak? Planar diagram. And so far it was planar cover graph. Well, this is the moment we have to draw some posets here. Yeah. Here is a nice looking poset. Here is diagram. There is no way to draw this diagram in a planar fashion. Absolutely no way. But the cover graph of this poset is planar. So when we say that poset has a planar diagram, we say more. We can take it to the extreme. Here is a very nice example given by Tom some years ago. It has a planar cover graph. The relation goes like inwards of the poset. Yeah? It induces a standard example. Look, this is the upset of A1. It hits all the B's but one. Okay? And what's more? We can plug 0. And now the head explodes, yes? Because planar with a 0, dimension at most 3. Planar diagram with 0, dimension at most 3. Planar cover graph with 0 and 1, and all the flowers. Yeah? So that's different. Yeah? And then in the planar diagram situation we have a linear upper bound. Kelly gives you a lower bound, yeah, for height, which is something like h minus 1, h plus 1, something like this. So it would be here only about the multiplicative factor. Yeah, speaking of multiplicative factors, it was a bit of surprise to us to see that it's not 1, yeah, which would be a first guess, yes. We can get dimension to grow like 4/3 of h, and this is how we do it in a planar diagram situation. So in a more restricted situation, yes, you see there is this nice gadget. You have a standard example of size 6 here. Yeah, for example, A2. It should be below all the B's, but the B2, which is over there. A6. Again, it's below all the B's, yeah? This B, and all the 3 B's above, except B6. And now, when you put this gadget inside, such that the outer vertices coincide with the inner vertices, and you iterate, what you do, if you look closer, is that you increase the height by 3. Every step. Height goes 3 up. It's something elementary to check. Trust me. But the size of a standard example that we built here goes up by 4. Yeah, there's a S6 here, but you know, one pair is used for gluing with one old pair, so effectively on each step we add +4. +3 in height, +4 in the standard example number, which this gives us a lower bound on the standard example number and dimension 4/3 h. This is the best we know. In a planar cover graph situation, we are a little bit more flexible and we can do the double wheel. This is a double wheel. Oh, it's almost a wheel construction. Yeah. So now it goes outwards. Sorry for that. It's a bit inconsistent. Yeah. So A's are inside and the relation goes outwards towards B's, which are, and then we connect one A's with other. So these A's from here, they go out through this and through this vertex, and they hit all the B's here. And the other A's from inside use this connection outside and hit the other B's. So it's almost all the wheel, but one space is left here and here to realize these connections outwards. It's 2h minus 1. This actually might be the right answer. There is something in this example that makes me believe that it could be it. But that's what we know so far. The most interesting thing here is the asymptotics that is open, and it would be great to see it linear. We cannot be sure, obviously, but it's something that we leave open, really, this possibility that maybe it's not linear. And then there is an example that we really haven't seen yet, something new, which would be great. This result with recurring numbers, it gives us a number of conclusions, because there are bounds for recurring numbers. Yes, I don't write you here the bounds for the recurring numbers themselves, because we're not going to discuss them in more details anyway. These are straight corollaries out of the things that we know from recurring numbers. So, for example, in the bounded genus situation, you have a single exponential bound, like in the planar case. The g is hidden in the multiplicative constant here, right? For g fixed, this is the bound, yeah? For t fixed, when you have a bounded three-way situation, this is what you get, 2 to the h to the t, yeah? And there is a lower bound of this style, which is an easy, which is an inspiration from this example that I just showed you, that has 3 at 3. If you can afford a slightly larger bags, then this is what you can do, and this is pretty straightforward, using this idea. No KT minor, that's the bound. Yes, so you see that dimension is bounded in terms of height, in a much broader situation. In fact, I already told you that the statement that is true here is that you can fix a class of bounded expansion, because these weak coloring numbers, they capture measures of sparsity that are studied, well understood. One of them is bounded expansion, the other is nowhere denseness, and these are not the definitions of these notions, but they could be. Yeah, there are lots of equivalent ways to say what does it mean for a class to have bounded expansion, and this is one of them. And then the corollary is, of course, that when you fix the class with bounded expansion, you have dimension bounded in the height. Now, when a class is nowhere dense, you cannot bound it by the height. But what you can do is something that people used to see in this nowhere dense business, is that whenever you fix your parameter, you get a bound that is growing in size of the instance, but in the style n to the epsilon, where you can take any epsilon that you want. And this actually is yet another definition equivalent way to say that C is nowhere dense. Yeah, given that the class is monotone, I need to have that the class is monotone to get this. Yeah, and I need it for the easy implication, which is usually the case, I think, in these kind of arguments. So what is not usual is...
The question, this is greatest epsilon less than 1?
Greater than 1, you say?
This doesn't mean anything if epsilon is big.
Yes,
so
exactly.
that's
I think it should say for all epsilon, actually.
Yeah, right, that would be nice.
Oh yes, wow, of course, for all epsilons. Every day there must be something like that. Yeah, it's for all epsilons, thank you, of course. Sorry for, I didn't read these quantifiers. I was just happy that they alternate. Yes, thank you. What is not usual in this setup is that we have a equivalence for lower denseness and we don't have it for bounded expansion. The usual way I've seen theorems were proven is that someone came up with a nice family of parameters that was proven that they capture bounded expansion, like neighborhood complexity, right? You like guys neighborhood complexity, yes? And then there was a proof that that this family captures bounded expansion, but the proof didn't give you lower denseness. You need to have another like insight, technical statement that supports the thing for lower dense. And then eventually you had another proof for bounded expansion. You could say that you understand better the whole picture. And this is not the case here because this is open for bounded expansion, and the reason is the implication that usually is the easy one, that no one spends time on. Yeah. So which implication is proven? Bounded expansion gives you this, yes, because from bounded expansion you have bound on the weak coloring numbers and you have bound on dimension with respect to height, but we cannot go back. We don't know how to do it, and even more, we actually suspect that there is something is going on there. And this might be nice combinatorics. There is this open field there that we didn't really, that we would like to enter, but we don't know how. We believe that the thing that would open the possibility to get a characterization for bounded expansion is this question here, that when you have a monotone class of graphs, take bipartite. Bipartite graph that had bounded dimension. This should be explained. So when you have a bipartite graph, you can read it as a poset. Yeah, minimal elements, maximal elements. That's what I mean, dimension of it. Yes. And so when you have such a class of graphs, posets, then this graphs, and when dimension is bounded, absolutely, then this should mean that the average degree there is bounded. There is a way to restate it. So instead of dimension, you can take boxicity. This is the way we solve this problem when we are in the graph theory meetings. It's absolutely, well, it's in the two-factor, multiplicative two-factor, boxicity and dimension in the height 2 case. So it's really the same question. And the problem that was posed on a number of workshops already by now is the following, that it's more or less a contraposition of the conjecture. So for every d, there exists f of d, such that if you take a graph, and you can get down to bipartite, if you take a bipartite graph of minimum degree at least fd, then you have a subgraph with large boxicity. Or then you have a subgraph that when you look at it as a poset, it has large dimension.
Can you explain boxicity?
Oh my god. Do you remember it, Michał, yourself?
No, that's why I'm asking.
Okay. So boxicity of a graph is a minimum integer d such that you can realize your graph, you can send vertices of your graph into boxes in R to the d in such a way that the graph is an intersection graph of the boxes. Axis aligned boxes, yes, thank you. Yeah, so you send a vertex to intervals on each axis. And then adjacency is when the corresponding box of one and the other intersect. Yes,
So
yes.
is it a subgraph or is exactly realized like this?
Exactly. That's my guess.
So it's not monotone.
It's not monotone. Does anyone know for sure the boxicity?
Yeah, I mean, it should be like the dimension is not monotone.
Yes, it makes sense. Yeah, now I'm sure as well. Yes. So why can we get down to bipartite? Well, when you have a graph with large minimum degree, there is a subgraph of a bipartite subgraph with large minimum degree. That's why bipartite is the thing here. Very good. This is exciting stuff. I would really like to take it on back to my research, but here is another very exciting stuff, dim-boundedness. Recall when you have a subset of incomparable pairs, we say it's reversible if the subset has no alternating cycles. And then you can build a hypergraph. Given the poset, you can build a hypergraph. Vertices of your hypergraph are incomparable pairs, and edges are on these incomparable pairs that constitute an alternating cycle. And now when you think about a proper vertex coloring of this hypergraph, it's nothing else like partitioning your incomparable pairs into reversible subsets. So the chromatic number of your hypergraph actually is the dimension itself. And when you look at the cliques in the hypergraph, maybe we should say what do we mean by cliques, but a set of vertices such that every subset of size 2 is an edge. Then there are standard examples. So yeah, so this supports a little bit this theory that we provide all the time, that dimension is like chi and standard example number is like omega. And the class of graphs is chi-bounded if there is a function f such that for every g in the class chi of g is bounded by f of omega g. The class of posets is dim-bounded if there is a function such that for every poset with a cover graph in the class, dimension of the poset is bounded by a function of the standard example number of the poset.
It doesn't see a class of posets.
Yeah. Sorry, I should say for every p in the class of posets. Yes, thank you. This is the conjecture. Maybe one of two conjectures that I really care about. Lots of stuff is exciting, but this is the one. Posets with planar cover graph are dim-bounded. It's open. Yeah? Why no one studies chi-boundedness of planar graphs? Because chromatic number is bounded, yeah? But in posets, dimension of planar posets is unbounded, which leaves room for this very exciting thing. And it's open. First published reference is here. Page 119, Tom, right? Where we can read. Also, comma, but let's leave this. I don't know of any natural conditions on planar posets which would bound the dimension. Although I expect that ruling out large standard examples is supposed it suffices. So this was clearly 20 years before you proved that if you don't have a chain, then dimension is bounded. I would say it's natural. But yes, this is as far as we know the first printed reference. But if you talk with Tom, he will tell you that the discussions like that were natural and appeared already when people developed the first examples, meaningful examples. So Kelly and your example from 78. There's not much to say here. There's not much to say here. Some years ago we took an angle that to do it from the sparsity side. So we took sparse class with structure, yeah, and we were able to do posets with cover graphs of bounded path width. Yeah. So please recall Kelly examples have path width 3, so you can have really complex stuff here. Dimension can grow, but if it grows and path width is p, then it grows with standard example number. Yeah? We are going to your question. Is standard example forced? Yeah? In the planar situation? Well, we actually don't know. When you have bounded path width, we do know. So it was never written and it won't be written. One reason is that that it was a little bit humiliating to write down a result about path width and to say that we cannot lift the argument to the tree decomposition, yeah, where we believe that it should be. But then we finally were able to prove it together with Michał. Posets with cover graphs of bounded tree width are dim bounded, and the critical insight is Szymon's factorization of trees labeled with elements of a semigroup, right? It's abstract thing. So you can decompose such trees that either a tree, a factor has a bounded height, or it's very uniform with some kind of Ramsey style uniformization. Well, the story is that within our arguments that we had before in the poset situation, it appears to me that we kind of developed something along Szymon's factorization, not knowing it, something weaker, yeah. And when we confronted it, we understood it. So then this thing really opened the possibility to lift the argument. And obviously it's much cleaner because if you use something from outside with an interface which is there written, then it forces you to actually spell out what you mean. Yes. So I hope we release it soon, right? No? There's one more development which I'm excited about. It's a case of a planar cover graph. So general one, with this one assumption that you have a unique minimal element, a 0. You have seen that dimension could be unbounded in the setup. And but if it grows, this statement tells you that there is a standard example that grows with it. And yes, we actually were able to get the bound twice the standard example number plus 2, and we believe that it's almost optimal, that the multiplicative factor is correct, and we are fighting with additive ones, and we are down to 2 or something like that, additive 2. So it's pretty satisfying, and we hope it will be of some use for the general problem. So that's for the dim boundedness.
So about the second theorem, I think we have presented in more so the same statement with bounded click width. Is there a problem there, or why is it here tree width?
Oh, there's no problem.
Okay.
I just thought that no one will know the click width, but obviously I'm wrong. Yes. This calls for. So there is a notion of a click width for a graph. And you can have click width of poset, the very natural thing to define in parallel. The nice thing about the statement for click width, I'm not going to define it here, but the nice statement, this statement, but with click width, is that you don't have a cover graph in the statement, which is really satisfying from this, from our perspective. Yeah, that it's really about poset itself. Yeah. Yes, definitely it will be given in terms of click width there. Okay, dim boundedness. So yes, here's the last little part of this lecture here will be kind of to prepare you for what is coming tomorrow. And what I want to do is I want to drop the sparsity business. I want to drop the planarity and show you that something more like not in the structure but extremal flavor of graph theory happens here as well. And so I want to show you the two theorems. Let's talk about this first one. The thing is that when you have a poset on n elements and you forbid a standard example, the dimension can grow. We've seen examples, but it's sublinear in n. And how should, let's try to relate to this statement. And the easiest way to relate for us is to look at the graph theory. Yes? So in the graph theory, you know, you have omega, you have chi, and if you don't have k free, so yeah, triangle free, this is what we used to say here. What can we say about chromatic number? Well, it's unbounded. We know several examples, but and usually that's game over. Oh, okay, unbounded, sorry, yes. But then, okay, but how large is it? How can it grow? Yeah? With shift graphs we've seen, log n, right? It can grow faster, yes? And and if you overcome this first statement and you inspect how fast it can grow, you can actually get a pretty good understanding of an easy proposition with an easy argument. So the thing is that it is big O of square root of n. Yeah? Have you seen this argument before? You color the vertices greedily. Well, what do you do? No, maybe not greedily. You look at your graph, and as long as you have a vertex of large degree, you look at it. Large means at least square root of n. Yeah, if you have a vertex of degree square root of n in your graph, V, what can we say about this neighborhood? It's an embedded set because it's triangle free. So we use one color here, second color for V, we take them out, iterate. Yeah? So as long as we have a vertex of large degree, we do that. And at the end, if you have something left, the degree is at most less than square root of n, so square root of n colors will suffice to color the rest. Yes? So how many colors did you use? You started with n vertices, and in every step like this, you took out square root of n vertices, at least, and you used two colors, yeah? So the number of steps is n over square root of n at most. Every step you use two colors, and at the end you apply some greedy coloring, another square root of n. This proves this proposition, right? So actually, this is not far from we know exactly what is the asymptotics of the maximum chromatic number of an n-vertex graph without the triangle, yeah? And it's theta n. This is the one, yes? I actually never read the lower bound. I don't know much about it, besides that it's a probabilistic deep stuff. It was a big thing in the 90s when people got this right. I know an explicit construction that gives you this. Maybe we do it in an exercise session. This is very fast growing comparing to the things we know. Michelsky, forget about it, log n, shift graphs, n to the 1/3. That's fast. Yes, so let me close the doors. Yes, so where are we heading with this? When we don't have KT, yeah, then things are quite understood here, in the sense that the chromatic number is n to the 1 minus ft. Ft is some function that is greater than 0, goes in a limit to 0 actually. Yeah? And from below you have another function with the same property. Yeah? So this is known here. There is some fight about these functions, and in general this is related to the so-called off-diagonal Ramsey numbers. Pretty deep stuff. So that's the graph theory perspective. What do we have on the poset side? Well, on the poset side we have a standard example number and dimension, yeah? And now when you forbid S2, we discussed that, that coincides with interval orders. Very nice objects, yet dimension unbounded. We exactly know the dimension, the maximum dimension of the asymptotics of an n-element universal or interval order, and it is log n. Yeah. Tom will tell you that we actually know much better the precision of this, but let's stick with the asymptotics here because I want to relate to that. What about S3? And this is the moment we realize we know nothing. So up to 2015, there was no upper bound besides saying n. Well, okay, maybe you could shave off n minus 1, but nothing big O of n. Yeah? And this statement tells you that it's sublinear. It's sublinear. Okay, nice. The statement here, the next statement gives you a lower bound. In the S3 free case, the lower bound is n to the 1 over 6 over log n, yeah? That's the asymptotics. So we have a polynomial growth, yeah? And from the upper bound, we just cut it from being linear. To understand the difference between this and this, let me tell you what I believe is the asymptotics in the S3 free. This is n times log n over log n. Well, yes. This is what we're going to see next time.
For S4, S5 and so on, you have just more logs.
Just more logs. Just more logs. Okay, more logs. Beautiful, nice statement, beautiful argument. Again, we would love to understand it better. We kind of suspect that the bound should be cut off polynomially, yes? We should have something like that, but we don't know how to do it. That's a great open problem. See you tomorrow. Thank you.